We're on a journey to the heart of the supermassive black hole, M87*. Our mission, to investigate one of the most mysterious places in the universe. M87 is a great target to visit because it's close and it's active, it's feeding. Supermassive black holes are the engines that power the universe. They're a key factor in the birth, life, and eventual death of galaxies. The more we study them, the more puzzling they become. They're the master key to most of the unsolved mysteries in physics. The physics inside a supermassive black hole are beyond weird. They are the final frontier of our understanding. Your imagination can run wild. Maybe it's even the source of other universes. There's only one way to find out. To go where no one has gone before and journey to the heart of M87. We speed across M87, a gigantic galaxy 55 million light-years from Earth. At its heart lies a supermassive black hole, M87*. It is the first and only black hole ever photographed. We want to find out how M87** grew so large, what lies inside, and how it controls the galaxy. 5,000 light-years out from the supermassive black hole. We get our first sign of the danger ahead. We see giant holes carved out of the galaxy. Starless voids, thousands of light-years. As we approach, we can see wreckage littered around the vicinity. It's like entering the lair of the dragon and seeing the bones of all the explorers who came before. What cataclysmic force tore these giant cavities in the galactic gas clouds? As we fly next to a brilliant shaft of energy, thousands of light-years from M87*, we get a clue. It's a deadly stream of radiation shooting out across the galaxy. A jet. This jet looks like a searchlight or a beam from a lighthouse. You're seeing this monumental thing screaming out of the black hole, blasting out radiation. In 1918, American astronomer Heber Curtis described the jets as a curious straight ray. A century later, observatory images reveal they pulsate with energy. The images show knots and clumps in these jets. They show that it's not smooth and nice, that there's been a history of violence inside this jet. This violent energy pushes the knots along the beams. The knots reveal the speed of the jets. It's like looking at a fast-moving train. Rail cars of the same color blur into one continuous image, but different colored cars stand out against the others. It's the same with the knots moving along the jets. We can figure out how fast the jets are really moving by looking at knots of material coming out from near the black hole. When astronomers measured the speed of two knots, they got a big surprise. One is moving at 2.4 times the speed of light, and the other is moving over 6 times faster than light. How could this possibly be? As weird as the physics around a black hole is, that's not actually happening, nor is it allowed to happen. Nothing can actually go faster than the speed of light. So obviously, we're missing something here. The knots may seem to break the speed of light, but the universe is just playing with us. It's really just a consequence of the fact that a lot of this jet is pointed toward us, pointed partially toward the observer on Earth. That, in a sense, is a sort of optical illusion that tricks you into thinking it's moving faster. It's a simple trick of the light. A bit like the way a spoon in a glass of water looks bent and distorted. The impossibly fast speed of the jet is just an illusion of perspective. From our perspective, it looks like the whole thing is moving towards us faster than light. But really, it's just cruising along very, very fast. The jets aren't actually breaking the laws of physics. They're pushing up against it. They're going at 99.999995% the speed of light. Imagine the energies necessary to accelerate this entire jet to that speed. So, what could produce enough energy to blast jets across the galaxy at close to the speed of light? There is a clue far ahead. The jets shoot out from a tiny, brightly glowing object. This is where things go nuts. This is the center of the action. This is where the real stuff happens. A ring of superhot gas and dust whirls around the supermassive black hole. It's called the accretion disk, and it shines a billion times brighter than the sun. If you had a ringside seat next to M87*, you would probably be fried very, very fast. But if you were some magical being and could survive anything, and if you had million SPF sunscreen and really great sunglasses, what you would see is this enormously bright vortex of gas swirling this dark void. This bright vortex spins around the supermassive black hole at over 2 million miles an hour. There's a tremendous amount of friction as material moving slower and faster rubs against each other. That's what's heating the disk up, and that's what's causing it to glow. Temperatures reach billions of degrees, making this one of the hottest and most electrically charged environments in the whole universe. This intense energy lights up not just the disk, but also illuminates our path across the galaxy. These supermassive black holes are some of the brightest objects in the known universe. They can outshine the light of all the stars in an entire galaxy by a factor of 1,000 or more. Such intense light clusters were first detected when we started to explore space with radio telescopes in the 1960s. Decades ago, astronomers began to see these incredibly bright sources in the deep sky, and they knew they were far away, and they knew they were bright. It made them the brightest things in the universe. Astronomers had no idea what they were. It wasn't until years later that we found that these bright sources were powered by giant black holes. Scientists think that the intense energy of the accretion disk is the source of the jets. The hot, swirling gas and dust produces powerful magnetic fields. As the disk spins, it twists up the magnetic fields at the poles of the black hole. Energy builds. Finally, the magnetic fields can't contain the energy any longer. They snap and blast the jets out into the galaxy. Even many light years away on the ship. We can see this violent release of energy. It's like the universe's biggest fireworks display. Two jets streaking out of M87 poles. One shooting away into the distance. The other racing past our ship. We're at a safe distance. Other things are not. When these jets shoot outward from the supermassive black hole, they don't shoot outward into nothing. If a jet hits a gas cloud, it annihilates it. It just punches a hole right through it. It's like a train going down a snowy track. The gas is like the snow, and the jets are like this freight train plowing across it. But here, a freight train traveling at close to the speed of light, smashing into clouds of gas, lighting our way to M87 as we follow the trail of destruction. There is evidence of similar destruction across the universe. In the Cygnus A galaxy, supermassive black hole jets have caused damage on a colossal scale. In many ways, Cygnus A is like a cosmic shooting gallery. You see this crime scene, this beautiful mess. When this jet comes out of the nucleus of Cygnus, it's going to encounter gas clouds. At that point, shockwaves set up, and this jet just rips right through this material, sending shockwaves in every direction, creating absolute chaos. It's hard to believe how much devastation these jets can cause. They're punching a hole in the gas, 100,000 light-years wide. That's the scale of an entire galaxy. As we head towards the center of the M87 galaxy, we enter hostile territory. The closer to the supermassive black hole we travel, the more dangerous it gets. As we approach the central core of M87, we start to feel it. All this energy, all this ferociousness is powered by that black hole. Intense winds start to buffet the ship. They push away vital gas, quenching star birth. Could these winds end up killing the galaxy and M87 itself? We're on a mission to explore the supermassive black hole, M87. First, we have to cross the M87 galaxy. It's 120,000 light-years across and it looks like a giant puffball. M87 is an absolute monster. It's a giant, elliptical galaxy. And that means that, as you go from the edges to the interior, you see a higher and higher density of stars. This vast galaxy contains several trillion stars. What's strange is that almost all of them are the same color. Your sky is covered with countless red points of light everywhere you look. Most of these points of light are small, long-living stars called red dwarfs. So, what happened to the different colored stars that we see in other galaxies? When you create lots of stars, you make lots of blue and red stars. But the blue ones don't last very long. They explode and are gone. The red ones, the ones that are lower mass, those are the ones that live for many billions of years. M87 hasn't made stars in so long that its stars are mostly red. We call galaxies with mainly red stars, red and dead. The only stars that are left in these red and dead galaxies are billions-of-year-old populations. Since it's not making new stars, the clock is ticking on M87. Essentially, it's a dead galaxy walking. The M87 galaxy hasn't made any new stars for billions of years. Something had to make that happen. Something had to deplete, or heat up, or push away the gas in those galaxies that would otherwise go into forming stars. We think that black holes in the centers of galaxies are the ultimate answer to this. So, how did M87 kill off star formation billions of years ago? As we cruise towards the supermassive black hole, we get a clue from the strong winds buffeting the ship. These winds can be incredibly powerful and really fast. You think a hurricane on Earth is bad. You should see some of these winds. Space wind is very different from wind on Earth. Earth winds are moving air. When the sun heats a surface on our planet, the air above warms and rises. Cool air below fills the space left by the rising warm air, creating winds. In space, winds are made up of gas and superheated plasma. The power that generates the winds lies ahead. The bright accretion disk surrounding M87, because it's so incredibly hot, it liberates an enormous amount of light, and that light can drive a wind. Black holes can power winds. They power winds with light itself. The more material that's falling into that accretion disk, the bigger and hotter it gets. And the more powerful the wind is that the black hole blows. We understand that light from the accretion disk creates the winds, but that is about all we know. We don't know that much about the wind. Is it expanding in all directions like a sphere, or is it aimed in jets? Very narrow and only moving in two different directions. Measuring the effect of the winds isn't as easy as you might think. It's not like going outside on a windy day and doing one of these. You have to infer what's going on with the winds by studying the light emanating from this object. Asterisk, we wanted to find out if black hole winds expand like a bubble or travel in narrow streams. So, we studied how iron dust from the accretion disk blocks the light driving the wind. Astronomers found the answer when they looked in the X-ray light spectrum. Asterisk, what they detected was iron absorbing those X-rays in every direction. They looked around the black hole. That's only possible if the black hole is blowing out a wind in every direction, which means that it is definitely blowing out a spherical wind, which is expanding into that galaxy. Asterisk, these black holes can almost literally inflate this growing sphere, bubble of gas that's outward flowing from the heart of the galaxy. These winds push out throughout the entire galaxy of M87, transporting heat and energy throughout the entire volume of the galaxy. Asterisk, what we found is that it's expanding away from the black hole at a quarter of the speed of light, 40,000 miles per second. Asterisk, for the M87 galaxy, that is bad news, because hot, powerful winds kill off starbirth. The winds can push away the gas that would have normally formed stars, so they can effectively quench star formation in a galaxy, causing it to gradually die. Asterisk, and it gets worse. In order for a galaxy to produce stars, it needs lots of gas and dust, and that gas and dust needs to be incredibly cold. Asterisk, hot winds from the black hole heat up gas clouds, so they can't collapse into stars. As M87 has grown, it has slowly shut down star formation. As the black hole in the center of the galaxy grows, it has stronger and stronger winds, and this means it's going to drive out more and more matter. That's what makes it a galaxy that can no longer support star formation. Asterisk, A supermassive black hole can determine the star formation happening in the galaxy. It can help to regulate the amount of gas in the galaxy, and therefore the number of stars that are formed in a galaxy. Asterisk, although M87 asterisk is tiny compared to the vast galaxy around it, it still controls its host. When you compare it to the size of the galaxy it's sitting in, it's like comparing a grape to the size of the Earth. To think that something so relatively small compared to the galaxy could have such a profound effect is just this remarkable illustration of how energetic a black hole can be. Asterisk, in the relationship between a supermassive black hole and the material surrounding it. The black hole is in charge. Asterisk, but not all supermassive black holes kill off star formation. The Phoenix cluster contains a supermassive black hole, but produces enough cold gas to form 500 stars a year. This is a place where we normally expect only to see hot gas. Here's the mystery. Why is all of this cold gas so far out in the galaxy? Asterisk, observations reveal that jets shooting out of the supermassive black hole inflate giant gas bubbles, 82,000 light-years through the galaxy. When the team superimpose a map of the cold gas over a map of the hot bubbles, they line up. Asterisk, there's something about those hot bubbles that are allowing cold gas to form on top of it. When the jets move out and inflate the bubbles, they drag behind a wake of slightly cooler gas. This colder gas starts to form more stars. Asterisk, the black hole can redistribute gas, and it can heat up gas, and it can also cool down gas. And so that way it can regulate the environment inside of the galaxy. Although M87 calls the shots, its past, present, and future are inextricably linked to its host galaxy. The view from our ship is endlessspace.com and unchanging. But the M87 galaxy has a violent past, a history of cannibalism, death, and destruction. Asterisk, we've traveled thousands of light-years across the M87 galaxy, but its supermassive black hole is still far in the distance. From our current position, M87 asterisk may look small, but it's 6.5 billion times the mass of the Sun. So, how did it get so big? Asterisk, one of the big mysteries we're still trying to understand is what controls how big the giant black holes at the centers of galaxies become. We know that it's tightly correlated with things like how big the galaxy is. Bigger galaxies have bigger black holes. To understand how M87 became so big, we have to investigate the history of its galaxy. We need to discover how M87's host galaxy grew so large. M87 is huge. It's a big galaxy with a big black hole. It's really big. It's what we call the brightest cluster galaxy. And these so-called brightest cluster galaxies are among the most massive galaxies in the known universe. Asterisk, usually, a galaxy with the mass of M87 is much smaller, but M87 is puffed up hugely. Why? Asterisk, one lead comes from the layout of M87's stars. As we travel through the galaxy, we see that the stars spread out over an area 100 times larger than expected. So, what scattered the stars? Asterisk, galaxies aren't static. Every galaxy is moving, and sometimes galaxies get very close and can interact with each other. Interact is a polite way of describing something extremely brutal. Asterisk, galaxies are colliding with other galaxies. They're cannibalizing smaller galaxies or tearing each other apart. Sometimes they're like drive-bys and they'll warp each other's structures. Sometimes the galaxies have head-on collisions and merge. Asterisk, merging pulls in new gas and stars. so galaxies grow larger. Galactic cannibalism is common. Maybe the M87 galaxy ate its neighbors. But how can we find out? Asterisk, we could try to identify stars that came from the consumed galaxies, but that's not straightforward. When you're trying to map out a distant galaxy, it turns out using their stars is a really hard thing to do. They smear in with the foreground and the background. Asterisk, it's actually very difficult to see any evidence that that galaxy merger ever happened. It's all smoothed out. It's kind of like throwing a bucket of water into a pond, and then asking after the waves go away to separate which molecules of water came from the pail of water versus which were in the pond. All you see is just mixed pile of water. And it's similar to that with the stars in a galaxy. Asterisk. So, how can you spot water from the bucket in the pond water? We need to detect signs of disruption, like ripples or distinct streaks of sand and mud thrown up by the disturbance. When galaxies merge, they may also leave a leftover that stands out, like a planetary nebula. Asterisk. Planetary nebulae are these bright beacons that you can pick out and map out the galaxy with great precision. Asterisk. A planetary nebula forms when a dying, mid-sized star blows off its outer layers after running out of fuel. These outer layers of gas expand, forming a nebula, often in the shape of a ring or bubble. You see this beautiful, glowing blue-green blob coming away from the star. These are so much bigger than stars. You can pick them out very easily. Asterisk. One team went planetary nebula hunting in the M87 galaxy. As they mapped the galaxy, they picked out 300 distinct glowing points. The points are blue-green, confirming their planetary nebula. Planetary nebulae are great. They really stand out like needles in a planetary haystack. The nebula's movements are distinct from the stars in M87. This shows they formed in a smaller, younger galaxy, not M87, because we see these planetary nebulae. Something must have happened in this old, dead galaxy. What was it? A galaxy collision. Asterisk. The discovery of the planetary nebulas shows that at some point in the last billion years, M87 ate a smaller galaxy. This galaxy strayed too close to the much larger M87. M87's powerful gravity snared the smaller galaxy and dragged it closer and closer. Asterisk. You could actually see this galaxy getting bigger and bigger in the sky, and it wouldn't stay the same shape. As the galaxy got closer, it would begin to distort, and your galaxy would distort as well, until the sky was filled with rivers of stars. Asterisk. M87 pulled in the small galaxy and swallowed it whole. Can you think of anything more dramatic than the collision of two galaxies? Asterisk. A violent history of mergers explains how the M87 galaxy grew so large. Each event brought in many millions of stars. The collisions also unleashed enormous gravitational forces, scattering the stars like confetti. Asterisk. After a collision like this, the stars are probably 10 to 100 times more spread out than they were before. Some collisions threw stars around, others changed the shape of the entire galaxy. Asterisk. If that galaxy merger is violent enough, it injects so much energy into the galaxy that the stars basically all move away from the center, and it makes the galaxy much more puffy, gradually transforming it into the smooth, featureless, elliptical shape. Asterisk. Most galaxies have a supermassive black hole at their center, including those galaxies eaten by M87. So, what happened to those black holes? Did they merge with M87 asterisk, increasing its size? Asterisk. M87. The fact that it's an elliptical galaxy also supports the fact that it's had multiple supermassive black hole mergers, which is how M87 could have gained its sizable mass. Compared to its violent history, the M87 galaxy is now relatively calm. We think that in the past, M87 asterisk grew by gobbling up other supermassive black holes brought in by collisions with other galaxies. But we don't really know, because physics suggests that supermassive black holes can never merge. Instead, they lock together in a cosmic dance for eternity. Asterisk. As we travel closer to the supermassive black hole, we pass the remnants of smaller galaxies eaten over the last 10 billion years. They reveal how the M87 galaxy got so vast. Most of these consumed galaxies probably had a supermassive black hole of their own. If M87 got so large by eating galaxies, did M87 asterisk get supermassive by consuming other supermassive black holes? Asterisk. When galaxies merge, all their stars and nebulae mix together. And then also, their supermassive black holes eventually find each other and find their way down to the center of the newly merged galaxy. Asterisk. Just like dropping two stones into a pond. They'll both reach the bottom. They'll both move toward the center, and they will start to move ever closer together. Asterisk. But do the supermassive black holes actually collide? We've witnessed the merging of smaller, stellar mass black holes, and we've seen supermassive black holes get close together, but we've never observed and merge. Asterisk. When galaxies merge, their central supermassive black holes should merge. The first step in the merger process, they're sinking toward the center of this newly formed galaxy. Asterisk. As they plunge towards the galactic center, The supermassive black holes plow through fields of stars and clouds of gas. They don't just run into each other, they inspiral toward each other, so they're going to scatter stars everywhere. And the closer they get, the more rapidly they will orbit each other. Things get even more chaotic and crazy. Asterisk, in all the chaos, something strange happens. The supermassive black holes stop moving closer to each other. This is a problem, and we call this the final parsec problem. Asterisk, so, what's going on? Why do they stall? Asterisk, the final parsec problem happens when two supermassive black holes run out of material to help them to merge. If there's not enough stars or gas that the black holes can interact with, it takes longer than the age of the universe for them to lose enough energy to merge. The black holes effectively stall at this final parsec of separation. Asterisk, the two supermassive black holes lock together in an eternal cosmic dance, close but forever apart. Asterisk, but some supermassive black holes must have merged. It's highly likely that many of the galaxies M87 swallowed had supermassive black holes. And yet, on our trip, we haven't seen lots of supermassive black holes, just IM87 asterisk. So, mergers take place. But how? Asterisk, in 2019, we got a clue from a galaxy called NGC 6240. This particular galaxy looks like the aftermath of a massive galactic collision. There are lumps and clumps of stars, random groups at random directions and random velocities. It's all mixed up, which is what we think galaxies look like after a massive merger. Asterisk, the merger aftermath reveals a more complex series of events than a two-galaxy collision. What we find in the center of this galaxy isn't two, but three giant black holes, which suggests that there have been three galaxies colliding in recent history. Asterisk, when this new galaxy starts to merge with the galaxy that hosts the stalled pair, it brings in its own third supermassive black hole. Now, this supermassive black hole perturbs the system, and it makes what's at the center highly unstable. Asterisk, the gravity of this third supermassive black hole steals orbital energy from the stalled pair, pushing them closer together. It's almost a thief that comes in and takes away some of that rotational energy from this binary black hole system. Asterisk, as the two lose orbital energy, the likeliest thing to happen is that the least massive supermassive black hole is ejected, and the remaining two merge very quickly. Asterisk, the high-speed merger will trigger a gigantic explosion. When these giant black holes merge, more energy is released in this process than our entire galaxy will emit over the course of billions of years. Perhaps M87 merged with other supermassive black holes in the same way a third black hole, helping it to overcome the final parsec problem. It's possible that mergers with other supermassive black holes allowed M87 to reach its sizable mass of 6.5 billion solar masses. Asterisk, supermassive black holes meet their match when they square off against each other. The fallout is cataclysmic, and as we get closer to M87 asterisk, our mission becomes more dangerous. We enter the gravitational kill zone surrounding the supermassive black hole. Asterisk, we know the dangers. Any unwitting stars that get too close are stretched, shredded, and torn apart, creating one of the biggest and brightest light shows in the universe. Asterisk, as we get closer to M87's supermassive black hole, we enter dangerous territory, not just for us, but also for wandering stars. If the black hole snares them, they are toast. But their death may solve one of the mysteries of supermassive black holes: how fast they spin. Asterisk, it's difficult to calculate just how fast a featureless black object hidden by a bright disk rotates. You need a lot of patience and a little bit of luck. Astronomy is sometimes a pretty opportunistic science. You have to be looking at the right place at the right time to figure out something new that we've never seen before. Asterisk, recently, astronomers caught a break when they spotted an extremely bright flare in galaxy PGC 43234. It was hard to miss. The flare was 100 billion times brighter than the sun. The energy output was absolutely ridiculous. If this happened in the center of our galaxy, it would have been so bright, we could see it during the daytime. Asterisk, a routine search for supernovas. Violent deaths of giant stars, detected the intense flash. ASASSN is this network of telescopes designed to look for brief high-energy events all around the sky, and primarily supernova. They saw a bright flash, and they thought, oh yay, another supernova. Asterisk, if you see a bright flash of light coming from a galaxy, that's kind of your first thought. Asterisk, but it didn't look like a supernova at all. It didn't act like a supernova flash would. It didn't have the right characteristics. It wasn't behaving like a typical supernova. It had to be something else. Asterisk, they sent out an alert to the astronomical community, saying, hey, there's something cool happening in this region of space. Once an event is flagged as real, then what happens is other telescopes turn their attention to that event. Asterisk, the data revealed something strange. After the initial flash, there are still smaller flashes that repeat. And if you're going to kill a star in a supernova, there's nothing left to repeat like that. Intriguingly, it flashed on and off about once every 130 seconds. The flashes continued for 450 days. Asterisk, when astronomers looked at this galaxy in detail, They saw that this event happened right at the center, and there's a black hole there with about 1 million times the sun's mass. And that was it. That's the smoking gun. Asterisk, what they observed was an extremely rare phenomenon, a tidal disruption event. Catching one live as it happens is an astronomer's dream. This was our first time catching a black hole in the act of feeding on a star. Asterisk, in galaxy PGCO 43234. A star wandered too close to a supermassive black hole. As this unfortunate star got close to the black hole is spinning, and the gravity around this monster black hole is so strong that it could pull the star apart. Asterisk, the side of the star, closer to the black hole, is feeling a much stronger gravitational pull toward the black hole than the far side of the star. Because it's farther away, what this does is it stretches the star. Asterisk, it got ripped to shreds, it got shredded. It got pulled out and stretched and whipped around the black hole. This stretches the star into some giant long arm, and that swirls around and is trapped as it orbits the black hole. The accretion disk snares the shredded star. What this means is that accretion disk is going to increase its output of radiation, in particular, high-energy radiation. Asterisk, as the star embeds in the accretion disk, a massive flare of radiation erupts, lighting up the universe. After this initial burst, the spinning star debris sends out a continuous stream of light. Our telescopes only pick up this radiation on each rotation of the disk. It's like seeing the beam from a lighthouse every 130 seconds. Asterisk, the flashes are the final pulses of a dying star, and those flashes reveal both the width and the rotation speed of the supermassive black hole. Asterisk, we learn that the central massive black hole is about 300 times wider than the Earth, but it's rotating every 2 minutes. It's rotating at half the speed of light. That's over 300 million miles an hour. Asterisk, we don't yet know how fast M87 asterisk is spinning, but we do know the accretion disk rotates at over 2 million miles an hour. This glowing ring, hundreds of light years wide, now lies directly ahead of our ship. It is one of the most awe-inspiring and deadly places in the universe, and we are heading straight for it. Asterisk, after our long trek across the galaxy, we finally face the mighty supermassive black hole. At its center, AM87 asterisk, a dazzling glare confronts us. This is the accretion disk, a ring of hot gas and dust spinning at over 2 million miles an hour. M87's accretion disk is so bright, the Event Horizon Telescope photographed it from Earth 55 million light-years away. Asterisk, the Event Horizon Telescope photo is the first picture ever taken of a black hole. The image revealed M87 asterisk spins in a clockwise direction, and it's 23.6 billion miles wide. That's around 3 million Earths lined up in a row. Asterisk, the photo also confirmed M87 asterisk's membership in a very exclusive club, the 1% of supermassive black holes that actively feed. The image from the Event Horizon Telescope tells us that M87 is indeed actively growing and accreting and eating material around it. It shows gas swirling around that black hole on its way to being swallowed. Asterisk, but do all supermassive black holes consume material in the same way that M87 asterisk does? Is it possible that different black holes have different table manners? Well, it turns out that's really true. Some are more delicate eaters. Asterisk, in 2018, we discovered a supermassive black hole, 250 million light-years from Earth, that eats on a schedule. Now, we have this case of a black hole that looks like it's feeding 3 times a day. It's having 3 square meals a day. Asterisk, intense bursts of energy pulse out from galaxy GSN 069. We see X-ray flares and bursts coming from the center of this galaxy, repeating every 9 hours, and each burst is associated with a new feeding event. Asterisk, this supermassive black hole not only eats on a schedule, it has a very healthy appetite. Each one of these meals that this black hole is consuming is the equivalent of 4 of our moons in a single bite. Asterisk, so, what exactly is this supermassive black hole consuming? The most likely contender is a star. We think that the star has been ripped apart and spread throughout an accretion disk, and then slowly, over the course of hours, an instability builds up, and some material falls in. Asterisk, when the infalling material from the star hit the supermassive black hole, it triggered a burst of X. Then, the system stabilized, until it sparked up again, creating a 9-hour cycle of bursts of energy. Asterisk, then, in 2020, new observations spawned a different theory. The star wasn't caught on the accretion disk. The supermassive black hole had instead pulled it into orbit. Its orbit takes it near that black hole every 9 hours, and every time it encounters the black hole, some of its material gets sipped off. Asterisk, eventually, the GSN 069 supermassive black hole will lose its meal ticket, but it's luckier than many other supermassive black holes. Asterisk, sometimes, black holes just take a little nibble on the surrounding material and just give a little burp of radiation in response. Asterisk, a black hole burp generates strong shock waves that radiate out across the universe. We detected 2 of these energy outbursts in galaxy J1354 plus 1327. located 800 million light-years away. The huge burps suggested that the supermassive black hole at the core of this galaxy was snacking. Asterisk. It ate a bunch of material one time that caused a burst of energy flowing outward. Then it feasted again. Asterisk. What caused these separate outbursts? The belching black hole galaxy has a smaller companion galaxy. A gas stream links the two galaxies, supplying an intermittent, on-off food supply. Asterisk. There's actually a smaller satellite galaxy going around the bigger galaxy. The black hole in the middle is pulling streams of material off this little galaxy. Asterisk. Clumps of material from the companion galaxy move toward the center of J1354. Once there, the supermassive black hole grabs them. Some gas, streaming from the neighboring galaxy, reaches the center when the black hole feeds and then ejects a jet. Asterisk. When supermassive black holes, like the one in J1354, receive an irregular supply of food, a cycle is established. A routine burp nap. M87 asterisk doesn't do burp and nap. It feasts all the time. Asterisk. Stars come in and get ripped apart, maybe once every 10,000 or 100,000 years, whereas M87 has been shining brightly for millions of years. It clearly has a supply of gas, other than ripped-apart stars, that's feeding the accretion disk. Asterisk. This helps explain how M87 asterisk grew to 6.5 billion solar masses. But what about the future? Will this supermassive black hole continue to feast, or will it starve? Asterisk. To find out, we have to move even closer, across the accretion disk, to discover just how M87 satisfies its insatiable appetite. Our ship passes over the accretion disk of M87 asterisk, a blazing ring of gas and dust, hundreds of light-years across. This is the supermassive black hole's grocery store. Asterisk. Black holes are known for sucking in everything. But is that really true? Asterisk. Black holes don't really suck. It's a popular misconception. They don't just pull anything in. In fact, if the sun just instantly turned into a black hole today, the Earth would happily continue on in its orbit, because all that gravity cares about is how massive and how far away something is. Asterisk. Supermassive black holes, like M87 asterisk, are a lot more massive than a regular sun-sized black hole. This means their gravity is greater and extends much farther out into the galaxy, allowing supermassive black holes to attract dust, gas, clouds, and stars from billions of miles away. But they don't gulp down everything they pull in. Asterisk. The way black holes eat matter isn't as straightforward as you might imagine. Earth gains mass every day from objects falling to it from space. So, you might imagine that matter falling onto a black hole is like meteorites falling onto Earth. They can come in from any direction and land anywhere. That's not the case around a supermassive black hole. The most efficient way for a black hole to consume matter is for it to grow an accretion disk. Asterisk. Accretion disks grow when gas and dust dragged in by the supermassive black holes. Gravity spirals inward and piles up in a ring. The ring starts to spin from the combination of gravity and the momentum of the gas and dust. The spinning material flattens into a disk. Asterisk. So, how does matter move from the accretion disk to the black hole? It comes down to friction and speed of orbit. Think of the International Space Station orbiting the Earth. The ISS has a low Earth orbit, between 200 and 280 miles above the surface. And at this height, there's still enough atmospheric particles around to produce drag and slow it down. If it slows down enough, it'll fall back to the Earth. So, we have to fire the ISS's boosters to speed it up and keep it in orbit. Asterisk. It's the same with accretion disks, but without the booster rockets. Matter within the disk spirals inwards because it loses energy and angular momentum due to friction. Asterisk. The material doesn't fall straight in. It orbits its way in, and so it gets accelerated to incredibly fast speeds. Sometimes, the matter ends up inside the black hole. Sometimes, the matter ends up getting kicked away from the black hole. Asterisk. As we traveled through M87, we witnessed jets and winds from the supermassive black hole blast this material out into the galaxy. But there may be other things that stop food from entering a black hole. Asterisk. The black hole, at the center of our Milky Way galaxy, what we call Sagittarius A, asterisk, appears to be swallowing material or eating at an incredibly low rate. To discover what's stopping Sagittarius A, or SAG, A asterisk for short, from feeding, scientists studied infrared light moving out from the supermassive black hole. To do that, they needed to fly high in Earth's atmosphere. Asterisk. The problem is, water vapor in our atmosphere prevents the infrared light from space from getting down to the ground. SOFIA is an infrared telescope built into the side of an airplane. As bizarre as that is, it's a very stable platform. SOFIA can look at these objects emitting infrared in space and get really good observations of them. Asterisk. SOFIA focuses on the structure of the gas and the strong magnetic fields at the center of the Milky Way. This high telescope can track the finest grains of dust. Asterisk. When all the dust grains in a cloud are aligned by a magnetic field, they scatter the light coming at them in a certain way, and we call this polarized light. The dust grains can actually map out the magnetic field embedded in that dust cloud. Asterisk. The telescope picked out the grains, arranged in a spiral pattern, and revealed the direction the grains were moving. This movement reveals why Sag A is starving. The magnetic field is channeling them into orbit around the black hole instead of allowing them to fall in. So, it's literally keeping those dust grains away from the black hole. Asterisk, the magnetic fields also pushed clouds of gas. Sag A, asterisk's food source, away from the supermassive black hole. This is the situation now. But that's not necessarily the way things are always going to be. Asterisk, because magnetic fields can switch directions. There's a lot of other junk out there, dust and gas and other stars, that as they get close, they can change the magnetic field, and that might allow that dust to fall into the black hole. Magnetic fields changing direction offers hope for Sag A, and magnetic fields could help M87 feed. Our mission continues. Following this material, plunging down into the supermassive black hole, we set a course towards the event horizon, the boundary between the known and the unknown universe, where the laws of physics no longer apply. Asterisk, our ship crosses the accretion disk. Ahead, the absolute darkness of the supermassive black hole, M87 asterisk. According to black hole legend, this is where we meet our end. Torn to shreds by gravity. Asterisk, we have so much wonderful imagery of what would happen if you were to fall into a black hole from science fiction. Asterisk, one idea that has caught popular attention is the notion that you get spaghettified when you fall into a black hole. Asterisk, so, will M87 asterisk spaghettify us? The answer depends on the black hole's mass and volume ratio. Asterisk, a stellar mass black hole with the mass of 14 suns is just 26 miles across. That's about the size of Oklahoma City. Such an enormous mass in a small volume creates a very sharp increase in gravitational tidal forces as you approach the black hole. With a small black hole, the strength of gravity changes so rapidly with distance that your feet could be pulled 1,000,000 times harder than your head. Asterisk, but with supermassive black holes, that doesn't happen. The mass of a stellar mass black hole is concentrated in a small area. A supermassive black hole's mass spreads much wider over an area 1,000,000,000 times larger. So its gravity increases gently as you get closer. This means approaching a supermassive black hole feels more like walking down a slope rather than jumping off a cliff. So it won't rip you to shreds. Asterisk, supermassive black holes have a bad reputation. That bad reputation firmly belongs to stellar mass black holes that rips things to shreds. Asterisk, the nice thing about supermassive black holes is these so-called tidal forces are much weaker. Asterisk, so, we can approach M87 asterisk safely. Once there, we are faced with an eye-inspiring sight. The supermassive black hole distorts the light around it. Asterisk, far away from the black hole. That warping isn't very strong, but the closer the light gets to the black hole, the more severely its path is distorted, and the starlight around the black hole becomes really bizarre. They get stretched into rings and arcs. Asterisk, we can even see things hidden behind the supermassive black hole. Black holes can even bend light so it comes around and comes back on the other side. Asterisk, to really understand what's happening around a black hole, we need to understand gravity, and the language of gravity is the language of spacetime. Asterisk, spacetime binds the whole universe together. If we could put on special spacetime glasses, we'd see stars, planets, and galaxies floating on a grid of spacetime. These objects have mass, and mass distorts and curves spacetime. Asterisk, imagine a trapeze artist with a flat net underneath them. When they fall from the trapeze onto that net, it forms a dimple right where that trapeze artist is. The trapeze artist is like a black hole. The net is like the fabric of space and time distorting because of the mass in it. Asterisk, this distortion of the spacetime net by objects with mass is called gravity. Asterisk, the more massive you are, the more gravity you have, because the more you bend and stretch space-time. So, one trapeze artist may bend the net a little bit, but 100 trapeze artists will bend that net a lot. And good luck trying to walk across it. Asterisk, black holes don't just bend space-time, they can also drag it. In 2019, astronomers observed a black hole called V404 Cygni. Like M87 asterisk, it's active, blasting out jets. They noticed these jets wobbled in a motion called precession. Asterisk, the jet goes off in weird directions. It actually precesses around in the course of only a couple of minutes. Asterisk, the cause. As the black hole spins, it's a bit like stirring a spoon in a dish of honey. Asterisk, you could actually see that space and time itself are spinning. And that changes the orbits and even the physics of stuff around it. Asterisk, so, is M87 asterisk dragging spacetime around, upsetting orbits in any jets coming from its poles? Asterisk, in that case, you've got a couple of billion times the mass of the sun. But amazingly, we do see that. The jet seems to be wobbling around with a period about once every 8 to 10 years. The black hole is spinning, but not exactly aligned with the disk. M87's immense gravity bends space, forcing light to travel along the curves. But what does it do to the other half of the equation? Time. Einstein realized that time actually runs slower near a black hole than back on Earth. It's a process called gravitational time dilation. Viewed from a distance, our ship appears to move in slow motion. But what do we see on board the craft as we approach M87*? You would perceive time to proceed on normally. You'd look at your watch, and that second hand would be going around the dial, just like normal. But to an outside observer, that apparent 1 minute on your watch could take millions to even billions of years. And this is not some sort of illusion. Time really is going slower. So, when you come home, you would actually have aged less. Because time ran slower over there. On our final approach into M87, we reach a crucial milestone. We are now at the innermost stable orbit. We go any further, we're not getting out ever. You have two choices. You either escape to safety, or you fall into the black hole. Well, that's easy. We detach the probe to approach the black hole alone. You can think of the event horizon as being the surface of a black hole. But that's a little bit of a misconception. There's not actually anything there. That's just the distance from the center, where the escape velocity is the speed of light. Because nothing can travel faster than light. Nothing can escape a black hole. Think of the event horizon as a waterfall. If you imagine the flow of water over a waterfall, if you're a fish, you could swim up close to that edge and still escape. But if you go too far, you hit the point of no return, and you're going over. At the event horizon, the water moves faster than the fish can swim or our probe can orbit. So the waterfall, or gravity, carries them over and into the black hole. But what about the light around them? Imagine that fish that's going over the waterfall is carrying a flashlight. Say it's an alien fish. At a black hole, if that fish goes over that event horizon, not only does the fish and the flashlight get sucked in, but the light of the flashlight gets sucked in. There's nothing that can turn around. Light, matter, that passes through the event horizon can never come back out. It is a one-way ticket. A one-way ticket through the event horizon. Back on the ship though, we don't see the probe entered the supermassive black hole. Instead, from our perspective, the probe just gets slower and slower and slower and slower. Until it appears that time simply stops for the probe. Frozen by the enormous gravity of M87, the probe appears stuck, glued to the surface. But that's just our perspective. In reality, the probe has already crossed the event horizon and is inside the black hole. If only it was that simple. The two major theories that explain how the universe works don't work at the event horizon. General relativity says the probe enters the black hole, but quantum mechanics throws up some major hurdles. According to some ideas rooted in quantum mechanics, there may be something called a firewall, a wall of quantum energies that prevents material from actually reaching through the event horizon. The question of what happens to anything attempting to cross the event horizon has challenged some of the greatest minds in physics. Will our probe enter the supermassive black hole, or will it be burnt to a crisp in a wall of fire? Our probe is approaching the event horizon of M87, but there's a problem. The two major theories that explain how the universe works don't agree about what happens next. One says the probe passes through unscathed. The other theory says that's impossible. It suggests a probe hits an impenetrable barrier called a firewall. How can the same event have two different outcomes? There's a really interesting puzzle right now, which is where general relativity and quantum mechanics meet. And it's called the black hole information paradox. What we have is a very schizophrenic situation in physics, where we have two theories that just don't get along. Einstein's theory of gravity explains all the big stuff. Quantum field theory explains all the small stuff. So, which one is right and which one is wrong? This is the mystery. General relativity says, in theory, crossing the event horizon is no big deal. If you're passing through the event horizon, you wouldn't notice anything different. You can, in fact, cross the event horizon of a black hole like M87* in your spaceship without even knowing that you have. Nothing would change. You'd just peacefully drift inside. According to general relativity, our probe crosses the event horizon and enters the black hole. Quantum mechanics sees it differently. When it looks at the probe, it doesn't see a robotic spacecraft. It sees information. Everything at a quantum mechanical level has information. You can think of things like a particle having a charge. Particles have spin, angular momentum, and that information, as far as we understand, can't be destroyed. What do we mean by destroyed? Well, think of burning a book. The words are information. As each page burns, the words disappear. The information is gone, but not really. If you could track every single thing that was happening, track each smoke particle, put everything back together again, in principle, that information is still there. Because information can't be destroyed. The probe's information, even if mangled, should be inside the supermassive black hole. If the information that fell into a black hole just stayed locked inside of a black hole, that'd be fine. That doesn't violate any physics. But Stephen Hawking threw a wrench in the works when he theorized that, over time, black holes evaporate. slowly shrinking particle by particle, emitting heat known as Hawking radiation. Hawking radiation itself doesn't carry any information out, and Hawking radiation eventually destroys a black hole. Eventually, the black hole evaporates and disappears. As the black hole vanishes, so too does information about the probe. This is a big problem for quantum mechanics. Can black holes really destroy information? Even though quantum physics suggests you cannot. So, is the foundation of quantum mechanics wrong? This is the quantum information paradox. To try to prevent this impossible situation, scientists came up with a workaround, something that prevents the probe's information from ever entering the black hole. The firewall. Quantum mechanics says that there is this quantum fuzz causing there to be ridiculously high temperatures, literally burning you up as soon as you enter. If the firewall incinerates the probe, then its information will stay in the ashes of the ship, just like the words from the burning book. So, which theory is right? Does the probe safely enter the black hole, or does the probe burn up? The answer is, we don't really know. To find an answer, scientists have come up with some crazy ideas. One, called quantum entanglement, suggests that the probe is both inside and outside the black hole, its information carried by particles constantly popping up on either side of the event horizon. And Stephen Hawking, whose original idea that black holes lose information through heat, also came up with a solution. He suggested that black holes have soft hair. Traditional black hole science says they're bald, by which we mean that they have no features at all, except their mass, and their charge, and their spin that you can measure from outside. Hawking's updated theory says that black hole hair is made from ghostly quantum particles, which store information. Thermal radiation from the evaporating black hole carries this information away from the event horizon. If Hawking is right, the probe's information will eventually escape into the universe. The concept of black hole hair would solve the black hole information paradox if it exists. But we don't know if black holes have hair or if they're bald. Until we can unite quantum mechanics and general relativity at the event horizon, the information paradox will remain a problem for physicists. It's one of the most embarrassing problems in physics, which is still unsolved. The failure to solve the black hole information paradox throws up a major obstacle to our understanding of how our universe works. This is the point where physics hits a wall. While a search for a solution continues. Let's assume our probe dodges its way past the information paradox. It sails across the event horizon towards one of the most violent places in the universe, the core of M87 *. It's called the singularity, and there are no rules. Nothing makes sense. Our probe has crossed the event horizon. It's on a one-way trip to the heart of the supermassive black hole M87. Anything that crosses the event horizon is not coming out. It's like Vegas. What goes in a black hole stays in a black hole. The probe leaves the physics we understand and enters the world of physics we do not. This probe is now moving faster than light or being carried by space itself faster than light. Once you cross the event horizon of a black hole, your future lies on the singularity in the center of the black hole. There's no escaping the fact that you will eventually join the singularity. The space inside of a black hole is like a 3D spinning vortex. The space in there is always moving. This is the nightmare version of the carousel ride. The whirling probe hurtles downwards until it hits an even more bizarre region of the black hole, the inner event horizon. You thought the firewall was bad, but that's peanuts compared to the inner event horizon. Theoretical. Physicist Andrew Hamilton believes that all light and matter that's fallen into a black hole piles up in a tremendous collision at this location. The inner event horizon would be infinitely violent, because it's like the meeting point between two universes. This meeting point is like water falling and smashing into spray, shooting back up from the rocks at the base of the falls. Inside the supermassive black hole, space races in and crashes into rebounding space at the inner event horizon. This would be a place of infinite energy. It's a place where infalling material into the black hole meets outflowing material. Everything falling into M87 smashes together in a monumental release of energy. This energy has got to go somewhere. It's possible that this inner event horizon is so energetic that brand new universes could be born in this space. But the question is, how do you actually birth a new baby universe? The energy created at the inner event horizon could compress down into one tiny speck, which suddenly ignites, sparking baby universes into life in their very own big bangs. We know that, a long time ago, our own universe was very small, very hot, and very dense. It's possible that it could have been born in the inner event horizon of a spinning black hole. This is such a tantalizing and very hypothetical idea, but if it's correct, it gives us insights into the origins of our universe itself. Do we have strong evidence that black holes create baby universes? No. Do we have strong evidence that they don't? No. Asterisk if the probe survives the inner event horizon, it then heads towards the strangest place in the universe, the core of a supermassive black hole, the singularity. Asterisk as the probe gets closer and closer to the singularity. The probe gets further and further away from known physics. We don't know what the probe will encounter when it reaches the singularity. We don't know what it will find. We don't know what it will experience. We don't know. Asterisk in other words, there's a lot we don't know. Like what exactly is the singularity? It's a hard question to answer. Asterisk traditional science says it's an infinitely tiny point, but that's not the case with M87. What's interesting is that if your black hole is spinning, the singularity is not a point, but it's, in fact, a ring. Physics says the singularity is infinitely dense. A point of space and time that is it's collapsed as far as it will go. It basically has infinite density in zero size. Asterisk for many scientists. That's a big problem. Asterisk, the word singularity sounds so intimidating and scientific, but it's honestly just our physicists' code word for, we have no clue what we're talking about. Asterisk, where else in nature do we find we're talking about a region that would have infinite density and infinitely small volume, basically zero volume. How could that exist? Asterisk, we just don't know, and frankly, we will never know for sure. Perhaps the probe breaks up and joins material consumed by M87 over billions of years, compressed down, not just to atoms, but to a sea of energy, absorbed into a ring of zero volume and infinite density. Asterisk, or there could be another possibility. Asterisk, it could be that the singularity isn't the endpoint of the probe's journey. It could be that the probe passes through the singularity and enters into a new universe. Asterisk, our probe has another option, an escape route out of M87. In our universe, we have black holes, objects where, if you enter, you can't escape. It's also theoretically possible for there to be white holes, objects that you can't enter. You can only escape from. Asterisk, a white hole is basically a black hole running backwards. Asterisk, some physicists have theorized that white holes may link to the singularities of black holes, connected by something called a wormhole. Asterisk, there have been interesting papers written suggesting that you could have a wormhole where something that falls into a black hole here comes out of a white hole somewhere else. Asterisk, it sounds like a great way for the probe to escape certain death. Theoretically, a wormhole is the bridge in spacetime between those two things. It's easy to create in mathematics. It very well might not exist in real life, and will almost certainly live out on our entire civilization, and never know about it. Asterisk, that's because constructing a bridge between a black hole and a white hole creates a few issues. Asterisk, we don't know how to build them for sure. They might be unstable and collapse on themselves immediately, unless you have some new weird sort of matter that can support them. Asterisk, the problem is that it's hard to maintain this bridge open. It's not likely that they would ever have any practical use because they're just not stable. Asterisk, but if M87 asterisk does have a stable wormhole linked to its singularity, where might our probe end up? Asterisk, it could be that this probe's journey doesn't end at the singularity, and all the information that it carries with it could be deposited in some distant corner of our own universe. Asterisk, or perhaps in a different universe. One idea that sounded like science fiction decades ago is actually now considered potential reality. And that's the idea of parallel universes. If parallel universes exist, then some surmise that a black hole could be a gateway to a parallel universe. Asterisk, if there are parallel universes, who knows which one our probe may end up in? This universe may be just like our own, or it might be something completely different. Asterisk, we'll never get to find out unless we follow in after it. It could all work out just fine, and that probe just sails on through and gets to explore new adventures. We don't know, only the probe knows. Asterisk, supermassive black holes are some of the strangest and most fascinating objects in the universe. Ever since Einstein's theory of relativity predicted black holes a century ago, we've been trying to understand how they work. The photograph of M87 asterisk confirmed many theories, but there is still much to learn about the birth, life, and death of these remarkable objects, and even more to leave us fascinated. Asterisk, this is the ultimate unknown. This is the real Wild West. This is the frontier of human knowledge. Asterisk, supermassive black holes offer us a truly unique window into how the laws of physics work, especially the laws of gravity in extreme regimes, far beyond anything that we can possibly imagine here on Earth. Asterisk, supermassive. Black holes lurk at the heart of almost every large galaxy that we know of. So, in some way, we're just sort of all along for the ride with the supermassive black holes.